All right, so we have two parts of lab today. The first part, I'm going to go over the acoustic startle experiment that you guys did the very first week of class. And normally, in our non-COVID world, you'd be recording that data this week and analyzing it, and then we'll do stats next Wednesday in our regular lab section. But since we were concerned if we'd be here or not, which we made it, great, congratulations, we went ahead and recorded that data earlier. So this week, all you have to do is analyze that data for lab, like you did with the EMG data. So I'm going to go over how to do that. And then after that, we're going to have a lecture on hormones and reproduction and emotion. Kind of get us ahead, because we're kind of racing against that Thanksgiving break deadline. And then tomorrow we will talk about stress. We'll talk about stress in learning and memory. And we'll talk about the stress system in general, but then specifically we'll talk about stress in learning and memory and stress in the immune system. So the first section of this class, I'll say that for when we get to the lecture part. I gave back exam 2s, and overall, the class average went up 6 points, which I was really happy with. And so I think everybody's sort of getting in the swing of things and knowing, like, this is a content-heavy course. I told y'all the very first day. There's a lot of information in here. You really got to learn it as you go, and I'll emphasize that, right? I think that it starts to get a little bit easier in the third and fourth section, because a lot of the information is more applied. We start talking about systems as opposed to like details, right? And there's still details within the system, but we start talking about learning and memory and stress and emotion, things that are sort of bigger picture types of things, right? And disease states. Okay? Overall, I am happy with the way that the class is going. I know I read through your exam 2 reflections, and I know several of you had issues with learning the sensory systems and the homeostatic systems. And my whole point about testing, if I didn't have to get a test, I'd be fine. Like, we could have no testing here. Everybody learned the material, great. But you have to have a way to show me that you learned the material, right? And so that's the whole point of testing. That's why we do tests. I don't like tests. I really don't like grading. But I just need to know that you can demonstrate that you know that material. That's the only thing I care about, is that you leave this class knowing the material, understanding the content, because this is like really your one foundational course in neuroscience that you're going to get in your psychology major here at law. And hopefully you're starting to learn the importance of understanding neuroscience in the brain for whatever sort of thing that you want to go into, how important it is, right? So, with that said, I also forgot or failed to mention or whatever, for whatever reason, the study guide that I had on here, and it was posted on here, I just didn't really highlight or point that out to you all. Although I did suggest, like, multiple times, that you guys make tables of the sensory and the homeostatic systems, which is essentially all this is a table, right? With all the things in there that you can fill out for the different sensory systems and for body temperature and for thirst, and the different areas of the hypothalamus, which is what I sort of suggested that you do. So one of the things that I thought, since in a lot of your reflections you wish that you had learned some of this stuff better than you had learned it, was I'm willing to give you guys an opportunity, if you didn't do as well on those sections, the sensory systems testing and the homeostatic systems testing, to demonstrate to me that you can learn it, or you did learn it, okay? So next week, I thought I had the date in my head, but now I'm blanking on when I'm available. I will send an email out with all the details of this, right? But I'll give you an opportunity to earn back some points on those 2 questions. But it will involve being able to fill out that study guide without notes from memory, completely. That's what you'll be grade it on, because that's all I want you to do. If you know the information that in all those tables, then you learned it. Good. And that's all I want to see you demonstrate to me, okay? So I'll give you some opportunities to do that, and I'll give you an email either today or tomorrow with the details of when and where we'll do that. Yes, Amy?
So would it be the whole study map that you just showed, or just like one or the other that was?
You can choose to do the sensory systems or the homeostatic systems, or both. Okay? And you're not going to earn back all your points that you missed, but you will have an opportunity to earn back some points if you can demonstrate to me that you do in fact know that information. Does that sound fair?
Yes, sir.
Because all I want to do, I just want you to know it, right? And I definitely want you to know it by the final, because we do have a cumulative final, and so that's part of why I ask you to write those exam reflections, is so that you know what it is you need to make sure you focus on making, learning that you identified in taking the test. Hey, I wasn't as clear as I thought I was on those things. Okay? Great. Super. All right, let's get to it. Oh, and I will point out that your next exam, exam 3 in here, is Thursday, the last Thursday of October. So it's only a couple of weeks away. We're going to cover, these are all the things that will be on that, right? So today we're going over reproductive behaviors and emotion. It'll, stress is part of emotion, so emotion is kind of broken into emotion. Talk about today is different than stress. Stress, we'll talk about biological circadian rhythms and sleep and dreaming and its relationship with memory formation, and learning and memory and dimensions. So all that material we're going to cover in the next 2 weeks, and then you have exam 3. So again, critical to stay on top of this. Do your review points after every lecture. Ask questions as you go. If you don't understand something, that's the time to get it cemented in your head. So when time comes for review, that you guys are ready to go on that stuff. Good?
Will it be study guide for exam 3
or no? No, not like that. Just your review points. Right? Just your review points. All right. So, part of this lab instructions is that there is some lecture content here, and this stuff will be included on exam 3. Okay? So the stuff that I'm about to talk about with habituation and sensitization and the aplasia model for that will definitely be on covered on the exam. So here are your review points for content from what I'm about to cover for lab, and then we'll get into the lecture part. Okay? All right. So we're going to get to talk about learning and memory in here after we talk about emotion and stress. So next week we'll talk about learning and memory. But we need to go ahead and talk about some learning and memory, some basic principles of learning and memory, so that you can write your method in your introduction, which is a draft of that is due next Tuesday. Start a class for peer review, just like last time. Okay? We're going to define learning in a very, very basic way. We're going to define it as any change in behavior as a result of some experience. So you have some experience, it changes your behavior, you learn something. Okay? 2 types of very basic, really subconscious types of learning are habituation and sensitization. So habituation is simply a decrease in a response that's presented repeatedly. The more times you present that response, the more times you present that stimulus, the weaker the response becomes. Thinking back to the acoustic startle lab, can you think of an example of habituation in that? Yeah, so you had a tone, acoustic startle tone, that was repeated over and over again, and the first time you probably responded pretty strongly to it, but as you began to be familiar with that tone, you probably responded less. Habituation. Okay? That's what we're going to measure in this lab. Sensitization is where there's an increase in the response to a stimulus, usually based on exposure to some other intense stimulus or change in your emotional state. Can anyone think of an example of sensitization from the acoustic startle? How many people had stimulus 1? Do you remember what it was?
The screen.
What?
Like the screen?
Yes. So we had 2 stimuli. We had stimulus 1, that at the 5-minute mark, there was a loud human scream. Right? Was that an intense stimulus, those of you that had it? Right? And so we're interested, did that produce sensitization? So on the next acoustic startle response, did your response increase as a result of having heard that scream? What about those of you in stimulus 2? What did y'all get at the 5-minute mark? You didn't get a scream. What happened? 6 weeks ago. Does anyone remember? Halfway through, what happened?
Like a different kind of a beat.
Yes, a different background noise, right? So everybody had that white noise, kind of low noise in the background. In stimulus 2, that got a little bit louder. Was it enough to startle you? Was it anything like the human scream?
No.
No, right? So we're interested in, does the human scream cause sensitization compared to a change in background noise? Okay. All right. In order to study what happens neurally, like we can look at your behavior and we can look at your physiological response, your heart rate, your breathing, your autonomic nervous system, your sympathetic nervous system activation through galvanic skin response, right? But if we want to understand what's happening at a molecular level, we need an animal model. Unless any of you are willing to let us stick electrodes in your brain and all that stuff, but probably not. Okay? So one of the models that's very useful, remember we talked about you need to choose an animal model that will allow you to study the thing you want to study. Right? We talked about zebra finches as songbirds, good model for language. Right? Rats don't really communicate verbally, not a good model for language. Well, the aplasia happens to be a good model for studying habituation and sensitization because it demonstrates those behaviors, and it's a very simplistic model. So there are 2 components. This is like a C-slug, the aplasia. There are, and you can use this information also in your introduction when you're trying to explain habituation and sensitization, the molecular events that underlie it. So the aplasia has this thing called a gill, and the gill can withdraw. So normally it's out this far, but when the aplasia is startled, it pulls it in as a protective measure, withdraws its gill. It has this thing called a siphon. And there are neurons, relatively few neurons, connecting these things together. So we can go in and actually look at the changes. If we're saying learning is a change between synapses, we can go in and look at what changes are happening in a relatively simple model where we can identify what neurons are involved. Okay? So when we come in with a little water jet and stimulate the siphon with some water, that causes the gill to withdraw. Okay? We can also apply a more intense stimulus in the form of a shock to the tail that might cause sensitization, might cause a bigger response as opposed to the water stimulation. Good? All right. So, in habituation, your book kind of leaves out the role of interneurons, and we'll talk about those interneurons. But we have, as I mentioned, relatively few neurons. We have the siphon and a sensory neuron from the siphon to detect the water jet, and that hooks up to a motor neuron that causes the gill to withdraw. Relatively simple. All right? There are other sensory neurons coming in here, like from the head. If you if you send a water jet at the head, that can also come down here and activate the gill withdrawal. Okay? All right, so what happens is if you repeatedly touch the siphon, the first time you blow water at the siphon, there's a big withdrawal reflex. The second time, less big. Third time, less big. And then eventually, you blow water at the siphon and the animal doesn't withdraw the gill. That's habituation. Decrease in the response due to repeated stimulation. The animal essentially learns that that water jet stimulation of the siphon isn't going to be harmful to it. It doesn't have to keep withdrawing the gill. It's not a threat. Right? Now, if you now blow water on the head, we get a big response. So that change, whatever learning happened, is specific to the neuron that goes from the siphon to the gill and doesn't affect the neuron that goes from the head to the gill. It also means that the gill just didn't get fatigued from withdrawing and can't withdraw anymore because it's too fatigued, because it does it right here. What do you think happens now after we stimulate the head if we go back to touching the siphon? What are your options? One is that it'll go up again. Another response is that we have a habituation here, it would just stay low, right? Pretty much have two options, right? And it turns out that when we touch the head, that eliminates the habituation that occurred, the learning that occurred, and the animal has to re-habituate. It has to relearn that that's a safe stimulus. And this change here is actually the role of that interneuron that your book leaves out. So when this pathway gets stimulated, it has an interneuron that kind of erases the learning that happened here and it has to start over. Questions? Good. Habituation. All right, so habituation occurs at this synapse between the sensory neuron from the siphon and the motor neuron. And what happens there is if we go in and so this is the interneuron, not shown in your book. So when the head causes the activation, this interneuron eliminates the change, the learning that happened here. And the axon-to-axon connection, the heteroreceptor connection that we talked about, right? All these things come back. All right. So if we were to put an electrode in this neuron and measure EPSPs, and we were to put an electrode in here and measure action potentials, right? We can see that for every action potential that's released here, we get an EPSP. As we repeatedly have action potentials, can action potentials be stronger, bigger, or different? They're all the same, right? They're all the same. But as we repeatedly have action potentials, what happens to the EPSPs? What happens to these EPSPs? They're not summing because they're too far away. Are they staying the same? They're decreasing. So the decrease in the gill withdrawal is because the same action potential is having a smaller effect. A smaller effect. And it turns out that what's happening is, remember, when an action potential gets down here, it opens calcium channels, and calcium is the thing that causes neurotransmitter to be released. In habituation, the more times you stimulate this neuron, the less calcium comes in. Less calcium means less neurotransmitter release. So here you might have 50 neurotransmitters, and then 40, and then 30, and then 20, and less neurotransmitters means less EPSPs, even though it's the same action potential. And that's due to less calcium. So when I ask you to describe the molecular events that underlie habituation, it's slide 14. Less calcium coming in, less neurotransmitters, less response. All right, sensitization. If we now go in and we're not stimulating the siphon often enough, repeatedly, to cause habituation, just like once every 5 minutes, we'll just probe it. So we get this nice sort of common response, not seeing habituation every 5 minutes going in and stimulating. Now, we come in and we shock the tail with electricity. And that causes a bigger withdrawal reflex than just simply blowing water on the siphon. And now we're going to go back to every 5 minutes blowing the water on the siphon. What do you think will happen?
It's going to learn that that's the stimulus associated with something. So it's going to have a
Larger response. So remember, what was the definition of sensitization?
Increase a response to a mild stimulation after an intense stimulation.
Yeah, mild stimulation goes up after intense stimulation. That's what happens. Now when we go in, same little water jet, bigger withdrawal because of the sensitization stimulus, right? So think about this in terms of your lab. Repeatedly hearing that acoustic startle tone should cause your responses to get smaller. Hearing the scream should cause that habituation. Two things. It could either cause the habituation to go away if it's not a sensitization stimulus. If it's not a sensitization stimulus, it will just cause the loss of habituation. You have to rehabituate. If it's a sensitization, if it's intense enough to be a sensitization stimulus, then instead of this point being here, it's going to be way up here, right? Meaning sensitization occurred. Does that make sense? So y'all understand what we did with hearing those tones and all that stuff? That is real important. As you saw in the EMG lab, if you don't understand what we did, if you don't understand the premise of the lab, it becomes really hard to talk about, to write about. So now it's a question to make sure we understand how habituation and sensitization of the aplasia relates to the acoustic startle tone and our changes in the 5-minute. Good? Yes?
So we were testing for sensitization.
For sensitization with the screen, whether or not it just caused elimination of habituation or sensitization. For the tone, what would you predict? Change in tone at 5 minutes. Was that an intense stimulus?
No.
So maybe it's more like touching the head here, and it just causes an elimination of habituation, and we have to rehabituate. So can you think of hypotheses that you could write about based on what you now know about habituation and sensitization? Okay. Nora and Kate Reed, y'all good? Does this sound familiar?
Yeah. He's so right. Well, if you don't understand this, writing your lab report is going to be so hard. So take good notes.
Or ask questions.
Yeah.
Right? We design these labs to reinforce and interact with the course content. They're not just exercises we want you, like demonstrations we want to do, right? They're actually applications of what we're trying to learn. Okay. All right. Just like I told you, slide 14 was the molecular events underlying habituation. Slide 18 is the molecular events underlying sensitization. How does sensitization work? And it turns out when we have an intense stimulus, there's another interneuron. An interneuron simply means a neuron connecting two neurons, in between two neurons. This one, we call it a facilitating neuron because it facilitates this sensitization process, right? But it's just an interneuron. And so what happens is that the interneuron, when we have an intense stimulus, releases serotonin on the axon terminal of that sensory neuron from the siphon. And that serotonin, so here's the intense stimulus. So here we have probe, get an EPSP. Probe, we should get the same EPSP. But instead, we have an intense stimulus. Now when we probe, we get a much bigger sensitized response, right? That happens because of serotonin. Sorry. Right? Dr. Goodwin said 19, but it's 19 and 20, mainly 20. That's molecular events, right? Which is serotonin activates a metabotropic receptor, G protein. What do we say have G proteins do? What do we say metabotropic receptors? What's the point of them? What do they do to cells?
They activate a second messenger inside the cell.
Yeah, and what's their job then? What do they typically do?
Change the excitability.
Change the excitability of the cell. And that's exactly what happens. We're going to make the cell more excitable through this cascade of G proteins. And those are, we have cyclic AMP that acts on protein kinase A. But the end picture is that we're going to inhibit potassium channels. And in a neuron, you remember which way does potassium want to go? In or out? Out. So if we inhibit a potassium channel, what does that mean is going to happen to the inside of the cell? More positive, absolutely. And so if it's more positive in here, maybe the resting potential goes from, what's it normally? -70, but now maybe it increases to say -60. Because we're not letting potassium leave. So when an action potential comes down here, what's going to happen? Bigger effect or smaller effect? Bigger effect, because we've already made it more positive in here. So it stays positive longer. That means more calcium can come in. And if more calcium comes in, what happens? Right? Increase in neurotransmitter. Increase in neurotransmitter, bigger response, aka sensitization. Right? Yes, Michael.
Why did you say that more calcium enters?
Because the serotonin acts through this metabotropic receptor to close this potassium channel, and potassium can't leave. So these are potassium ions that have built up. And more calcium then equals more neurotransmitter. Who has their phone in here? I don't have my phone. You can take a picture of that and send it to me so I can post it. You can do it? Otherwise we won't have all these nice notes. You got it?
Yeah.
All right, send it to me and I'll post it on the movie slide. All right. That is habituation sensitization in the model of the aplasia with the molecular events that underlie it as it's related to the acoustic startle reflex experiment. All right, now let's talk about what happened in that. To your body, not the aplasia, but to you, right? Remember this, through the autonomic nervous system, we have two responses to physical stimuli. If it's an intense stimuli, it might activate our sympathetic nervous system, giving us that fight or flight response. Increased heart rate, increased breathing, increased skin conductance, because we start to sweat a little bit more. Parasympathetic is the return, is the opposite of that. So think about what might be happening. The first tone you hear, you get a little of this, a little startle. As you continue to hear that tone, parasympathetic nervous system takes over and calms this down, says, hey, you don't have to respond that way. We're going to be more calm. And you get habituation. All right, this is just kind of a overview of that, right? That if you continue to have chronic activation, we'll talk about this tomorrow when we talk about stress and the stresses effects on the cardiovascular system. That can be dangerous, right? In contrast, if you have too much stimulation of the parasympathetic system, you can slow the heartbeat down so much it just stops. All right. So if we want to measure emotion, physiological responses to arousal, there are 3 ways we can do it. Galvanic skin response, GSR, those were those electrodes in white that you put on the pads of your fingers. And they were measuring very small changes in sweat, which is associated with arousal state. Very, very small changes in perception and perspiration. We can also measure changes in breathing, getting faster or slower. And we can measure changes in blood pressure or heart rate. When we do all 3 of these at the same time, like you did, we call that a multiple polygraph test. Have you ever heard of a polygraph test? What do you call a polygraph test?
Lie detector test.
A lie detector test. Oh, what a horrible name. It's really not what it is. It's not a lie detector test. It's an autonomic nervous system detector test. Detects if you're aroused or not, but it doesn't detect lies. Right? You heard about the story where the cops were interrogating the subject and they took some wires and made it look like they were attached to the photocopier, and they put a piece of paper on the photocopier that said lie, and so every time that they asked a question, they just pushed the copy button and lie came out. They should not very smart stuff, right? I mean, that could be a lie detector test, but this is not a lie detector test. Right? Okay, I'll be real clear about that. The problem with measuring emotional response is that your body responds the same way if you're angry or fearful or happy. Right? Think about the next time you see your significant other or your parents or your grandparents if it's been 7 months, right? You're going to have the same arousal as you have if someone startles you. Your body doesn't respond. It only has one response, autonomic nervous system activation. Our brain interprets that response in different ways. But a machine measuring your GSR and heart rate and respiration can't identify what caused that to happen. Right? So about half of the time, lie detector or polygraph tests can't detect lies correctly. So, like, think about it here. Imagine if you were working in a bank and someone stole some money and they decided to give everybody polygraph tests. And these are the questions they're asking. What department do you work in? And you didn't steal the money, right? You answer, you're like, I'm a teller. Who's your supervisor? And Mr. Smith. Have you ever taken money from this bank? You didn't take the money, but do you think you're going to feel anxious when they ask you that? Even though you're innocent? And then you get this big GSR, you're like, no. Big GSR response. Because you're scared. You're not lying, you're scared because someone just asked you. That's a scary environment. Someone just asked you a scary question.
So I took nonverbal communication. We had like somebody come in and demonstrate polygraph tests and like how they actually do them. And they don't ask questions like that for that reason. Like,
Right.
That's not how they actually do polygraph polygraphs. They do like they start out like just like regular
What's
questions.
your name?
Yeah, like what's your name, and like go more through specific stuff, like what you did throughout that day, instead of asking things like that to see if like a normal thing about your day you're lying about what
Yeah.
you were actually doing that time.
Right. But, do you think it's stressful to be hooked up to a machine when you know that someone stole money and they're
That's
trying
why
to
they
figure
take
out
like
who
2
stole it?
hours so that you can calm down as they go through.
Right. So, that's an example. Who came and talked to you? Do you know?
I don't know, but Dr. Steinmetz was one of the professors for the class. He asked her about it.
But was it a law enforcement
Yeah.
person?
Yeah,
someone-
it was people who gave polygraph tests like for a living.
Yeah. So I also have some firsthand knowledge. I've testified as an expert witness in cases for polygraph tests, and not everybody does it that way.
Okay.
Some people have you come in, and within 15 minutes they're done giving the test, and they just ask you these direct questions. So there are good ways and bad ways to possibly do this, right? All right. Yes, Lou.
In our psych and law class, we're talking about polygraphs right now, and they showed, Dr. McQuiston showed us a video of a guy, and he learned how to like beat with polygraph,
Oh, yeah.
and he's like in jail now.
Yeah. Because think about it, if you want to beat a polygraph, what do you have to do?
Gotta have control over.
You can do one of two things. You can either so believe in your head that what you did wasn't wrong, that it doesn't activate your autonomic nervous system, so you're just a flat line. That's called being a sociopath. Right? It is, right? You have no empathy, you have no emotion associated with what you did, so you don't get any response. Or you respond to every question, even the ones that aren't trigger questions. And then they can't differentiate between when you actually respond and when it's just a regular
That's what
question.
he said. He would have his like clients. He ended up getting called because he hired 2 undercover cops hired him to pass something, and then they arrested him. But he said like for every question you just imagine like you're on the beach or you're relaxed, and then whenever it really throws him off, whenever you just like don't think about the question, you think about something else.
Yeah, people have been known to do things like put a tack in their shoe and then press it into their toe to cause pain, to like generate a response every time to a question. There's all sorts of ways to beat a lie detector because it doesn't measure lies. It
Yeah.
measures autonomic nervous system activation, right? And so polygraphs are not admissible in court, in criminal court, because they're not valid. They're not reliable measures of lying. And so half the time people are found innocent when they actually were guilty, and half the time people were found guilty when they were actually innocent on the basis of their responses to polygraph tests. Fine. We're good. So, recognize this? What are we looking at? This is your stimulus, right? So we have that white noise, acoustic startle. White noise, acoustic startle. White noise, acoustic startle. This is stimulus 1. At the 5-minute mark, there was that scream. Then back to same tone, right? 6 times before, 6 times after, 1 change in 5 minutes. I don't think I have a picture of the other one. The other one, instead of having the screen here, this green line gets about that much bigger there and goes across, right? The baseline noise got bigger. Good? All right. When you pull up your data, this is how to do your data analysis. Now we're getting into how to do the data analysis, okay? And the instructions for this are printed out and by all the machines, and your data is on all the machines, just like the EMG. Okay? You should have, when you pull this up, you should have 1, 2, 3, 4, 5, 6 stimuli marked, your 5-minute mark, and then 1, 2, 3, 4, 5, 6 more marks. I don't know what this one is. Right? The EDA, that's your GSR response. Respiration in red. Average heart rate, so this is not your actual heart rate, but it's plotting a mean heart rate across there. Okay? things you need to do is first set up your channels here. And this is all written down in that paper. But the first one you're going to put on channel 3, peak to peak. The next one's going to be channel 40, BPM, that's your respiration, that's going to be breaths per minute. Channel 41, that's your heart rate. We want to know the average, the mean heart rate. And then the last one is, it doesn't matter what channel it's on, you just want delta T. Because that's going to measure how much time we've selected from the EMG. I've now taken data and zoomed in so I can see it better. And here we see 3 responses, some markers, right? I can see that a little bit better. All right, so peak to peak is going to be our measurement of GSR. We're going to measure how much did GSR go up. This peak to peak, bigger than this peak to peak, right? For breathing, we're going to look at, so you see there's cycles, right? We want to look at the bottom, the valley, that occurred just prior to that stimulus. Okay, that's how we're going to identify how we're measuring the breath. So we're going to look at this breath cycle. How far is it from here to that valley, from one valley to the next valley? All right. So what you need to do is go in, select from where the stimulus occurred and we're still at baseline, okay, past where the top is. Good? So you get your response there. If the response is like really big, that's fine. Just get, a couple seconds, right? And here we've actually selected 16 seconds. That's fine, right? Because we're only going to get from this point to that point for peak to peak. Right? This is important. So now we're going to record in our data sheet the peak to peak and the mean heart rate across that same period. Okay? On the website, there's an individual Excel sheet, just like last time. You're going to download it. It's going to look like this. Okay? We have 6 stimuli, 1A through 6A. We have your 5-minute mark, either the human screen or the change in tone. And then we have another 6 stimuli that are 1B, 6 through 6B. Good? We're going to take 2 measurements. Our stimulus measurement that we took here, we're going to take these numbers and we're going to put them in heart rate stimulus. So we're going to put in that 65.5 right here. And GSR stimulus 0.35. Okay? I'm not doing respiration quite yet. Now, we're going to go from that point where you started here, and we're going to measure the baseline for the same amount of delta T. So remember it was 16.2. Now we're going to start here and measure back 16.2. And we're going to put these numbers in here under baseline. So our heart rate now is 74.4. So you see it went up a little bit. Our baseline GSR was 0.03. You see it went up a lot. Okay? You can do that stimulus and baseline measurement for each stimulus and the change in 5 minutes, right? The screen or the change in stimulus and white noise, which will be a much more subtle change, right? Okay. All good on that? Yes,
Sorry,
sir.
so this is the baseline just after the stimulus?
Before.
Before, okay.
So here's the stimulus. Start where you started measuring the stimulus and go backwards the same amount of time. Over here in green, don't touch those values. It's calculating a percent change. Because everybody's resting heart rate's different, right? What it's calculating is how much percent change was here. So here, there was only a 2.7% change from baseline. Here, there was a really big change, right? 166%. Big change, right? These numbers here are going to automatically get transferred, that's the same number as this number, to the line in yellow. The only thing you need to do in the line in yellow is your subject initials, make it the right year, put whether you're male or female, 1 or 2, and whether you had stimulus 1, a screen, or stimulus 2, the change in baseline. Once you've filled out these figures here, all of those percent changes will be here. Then this yellow line is what you copy and paste into the Google Doc. Questions? Respiration. Respiration is slightly different. Respiration, remember, we're going to start at the peak, the valley, right before you get your response, right? And we're going to measure over to the next valley. And we're going to record that BPM here as our stimulus measure. Then we're going to look at the breath right before that, that same valley but the other direction, right? And record that BPM as our baseline. So that's how you do baseline stimulus for respiration. Good? This won't take long. It won't take very long at all. Okay? All right, that's it for lab.